Hi students, we were working on the 45 question review and we have 6 problems left to go here. So I'm going to start with problem number 38. The place to start is to write the KSP expression for each of the compounds. So you can see that I've written the KSP expression for silver chloride. Then I set the KSP value that's given, 1.8 times 10 to the minus 10, set it equal to x squared, x representing the silver ion concentration, and the other x representing the chloride ion concentration, because we know when silver chloride solid dissociates, it forms one silver ion for every chloride ion. And I recommend that you write the dissociation equations for B, C, and D, and then generate the KSP expression for each B, C, and B. The silver chromate, we have 2 silver ions for every 1 chromate ion. So that coefficient of 2 becomes the superscript 2. So, and we know that there are 2 silver ions. So this is 2x all squared times x, because it's 2 to 1, 2 to 1x. So this is 4x squared times x, that's 4x cubed, and now we solve for x. Let's write the KSP expression for silver phosphate. Now we have 3 silver ions for every 1 phosphate ion. Set the KSP value, 1.8 times 10 to the minus 18. Set it equal to 27x cubed times x, because 3 cubed is 27, and x cubed times x, so we have x to the 4th, and we get x is 1.6 times 10 to the minus 5. We'll do the same thing for D. Have the equation for the dissociation. We can write the KSP expression. KSP equals 4x squared times x. KSP equals 4x cubed. And we know the value of KSP. It's given 6.0 times 10 to the minus 51. Divide both sides by 4. Solve for x. Take the cube root. And so on. So the salt the question asks which salt will have the highest silver ion concentration. So the silver ion concentration, let's calculate that now. We go through these one by one. For A, the silver ion concentration is 1.3 times 10 to the minus 5th molar. For B, silver ion concentration is 2 times x, so that's 2 times x. So 2 times x, how do I want to write this more neatly? Silver ion concentration for B, since there are 2 silver ions, that's 2x, so that's 13 times 10 to the minus 5 molar, which is the same thing as 1.3 times 10. Make 13 smaller, make the exponent bigger. So there's our silver ion concentration, 1.3 times 10 to the minus 4. And for C, our silver ion concentration is 3 times, excuse me, let me fix that, 3 times, because there are 3 silvers, so that's 4.8 times 10 to the minus 5. And for D, silver ion concentration is 2x, and since x is something very small, we know it's something very small because the exponent is times 10 to the minus 51. So if we're looking for the salt that will have the highest concentration of silver ion, the winner has to be 1.3 times 10 to the minus 4. Right there. That's the biggest number of all the numbers. We were evaluating 1.3 times 10 to the minus 5, 1.3 times 10 to the minus 4, 4.8 times 10 to the minus 5, and then this number is going to be something wicked. This number is going to be something very wicked small. But for question 40, we're given the reduction equations and the reduction potential values for the reduction equations. And let's calculate E standard cell. Now, this is not an E cell. And I'm not going to do any sign switching. I use the values as given. I know that the more negative the number, the more easily oxidized. So I know that copper is going to get oxidized, and I know that iodine is going to get reduced. So this is the oxidation, and this is the reduction based on the values. More negative is oxidized, more positive is reduced. So we have the value is 0.016 volts for standard E cell. Hey, but they're asking us for K. So we did a problem like this in class. We're going to use E cell equals E standard cell minus RT over NF natural log of Q. Since we know that we're at equilibrium, that means at equilibrium, the cell does not operate. So E cell will be 0 and K equals Q. So you've got 0 equals 0.016 minus 8.314. Forgive me for being brief here. I'm not using units. Oh, I did for temperature, I guess. 2 moles of electrons, right? There are 2 moles of electrons. We would multiply this equation by 2 to get the 2 electrons. And Faraday constant, natural log of K, and then we solve for K, and I get K equals 3.48. If you're having trouble with that mathematically, getting that K value, just send me an email and we can do it out. I can send another video to do it out. Oh, wait, there was a question on 33. Let's go to 33. 33 is also a KSP problem. We are told that the pH equals 9. That means the pOH equals 5. That means the hydroxide ion concentration is 1 times 10 to the minus 5 molar. And the KSP, let's write the equation for the dissociation. It's some metal hydroxide, which is a solid, and it ionizes to some divalent metal plus 2 hydroxide ions. So now we can write the KSP expression. That's going to be some metal hydroxide ion concentration squared. So we know the concentration of the hydroxide ion. We've just calculated the concentration of the hydroxide ion. So the concentration of the hydroxide ion is 1 times 10 to the minus 5. We have to square that. And the metal ion concentration is going to be half the hydroxide ion concentration. So that's going to be 0.5 times 10 to the minus 5. 0.5 times, I know it's not proper scientific notation, but we're just calculating, so it doesn't matter. And this is 1 times 10 to the minus 10. So the answer is 0.5 times 10. When we multiply numbers, we add the exponents. So this is KSP, and putting it in proper scientific notation, take the 0.5 and multiply by 10. So we have 5. So if I make the 0.5 bigger by 10, I have to make the negative 15 smaller by 10. So this is our answer. And that is D. The answer is D. Okay, let's go on to 41. We're given a balanced equation. We're given the standard E cell of 0.743. So E cell equals E standard cell minus RT over NF, natural log of Q. We are asked to calculate E cell. We know the standard E cell because that's given to us, 0.743 volts minus 8.314. 298 is the temperature. We have to figure out how many moles of electrons. So that might have you stumped for a minute. So let me show you how I quickly think about the number of electrons here. They have kindly given us a balanced equation. So I'm going to calculate the oxidation state of manganese in the manganate ion. So this is going to be X minus 4 minus 2 because each oxygen is minus 2 and the charge on the species is minus 1. So that means X equals positive 7. So manganese is positive 7. We know manganese is positive 2 here. So that tells me that there are 5 electrons, right? To get from positive 7 to positive 2 had to involve 5 electrons. And the other thing you can think of is here you have 5 ions and each has a charge of 2 plus, so that's a charge of 10 plus. And here we have 5 iron 3, each with a charge of 3 plus, so that's 15 plus. So you can see going from 10 to 15, we would need 5 electrons on this side, and then going from positive 7 to positive 2, you'd need 5 electrons here. So I'm just kind of confirming 5 electrons, 5 moles of electrons, and 96,500. And now we have to think about the concentrations. So it's products over reactants. I'm going to assign the values here. Just making my little chart that this was given to us. These are the concentrations of the various ions. We're told pH is 3. That means the hydrogen ion concentration is 10 to the minus 3. And of course, there are 8 hydrogen ions. So I'm going to have to take care of all this. Products. So the manganese 2 ion. And then there is the iron 3 ion concentration, which we raise to the 5th power because there are 5 iron 3 ions, although 1 to the 5th is just 1. But just to illustrate what's going on here, the reactants, we've got 2.3 times 10 to the minus 2 for the manganate ion. And then we have for iron 2 ion, 1 right there, 1 times 10 to the minus 4. There are 5 of those. And then here we have 1 times 10 to the minus 3 for the hydrogen ion. And there are 8 of them, so we raise that to the 8th power. And then we just do the math. And all the whole business here, all of this stuff that we calculate, which is E cell, ends up being 0.20 volts. 2 problems left. Now 44. We have 3 metals, A, B, and C, and they're tested in a voltaic cell. So if you have A and B, and A is the cathode, that means that A is, you can think of it as A is the cathode. That means A is reduced. A is preferentially reduced, and that means B is preferentially oxidized. So if B is oxidized, B has a more negative standard E reduction, and A has a more positive E reduction. So we're asked, what they want us to know is the order of the reduction potentials. So we're going from big until small. So we're going from more positive to more negative. So what we've learned from the first statement is that the reduction potential for A, which is more positive, positive numbers are bigger than negative numbers, or more negative numbers, I should say, lower numbers. So that's what we've learned from the first statement. From B and C, C is the cathode. That means C is reduced, and B is oxidized. So what we learn from that is similar. C has a greater reduction potential than B. Because remember, in the reduction potential tables, we had positive values. There were a lot of equations, and hydrogen, the reduction of hydrogen was a value of 0, and then here we had all the negative values, right? So C is greater than B because positive numbers are bigger than negative numbers. And then with comparing A and C, A is the anode. So that means A is oxidized, C is reduced. So C greater than A. So we have a logic chain here, A greater than B, C greater than B, and C greater than A. So you have to string these together. So we really only need the last one and the first one. C greater than A greater than B. Right? C greater than A greater than B. See how there's like a pattern there. All right, let's go to 45. All right, so this is kinetics, and we have K's at different temperatures, or we have K at one temperature. There are two different temperatures, and we have the activation energy. So remember, this is the two-point form of the Arrhenius equation. And I think to use this immediately, whoops, I miswrote this. I think of you to use this immediately because they're giving us one value of K and they want another value of K. So I don't have to take the reciprocal. I'm going to say the unknown is K1 and the known is 8.54 times 10 to the minus 4. And negative sign. We know the EA. I'm going to turn it into joules though. You either turn EA into joules or you turn 8.314 into kilojoules. Either way. Joules, that's because 8.314 4 is in joule per volt, per mole volt. So T1, we're told, is 25 degrees. That's 298. Remember, we have to change it to Kelvin because joule per mole Kelvin, not volt. And T2 is 45 degrees C. Got to add our 273. So I'm just going to say that if you had wanted to, you could have kept that in kilojoules, negative 90.8 kilojoules, but put it over 8.314 times 10 to the minus 3 kilojoule per mole K. So we just have to make sure that we're keeping the units consistent. Doesn't matter what they are, as long as they're consistent. So we do our math, and we get K1 over 8.54 times 10 to the minus 4 equals e to the minus 2.05, which means that K1 equals 8.54 times 10 to the minus 5, reciprocal molarity, reciprocal seconds. So that's it. If you have any questions, you can email me, and I will see you on Wednesday when we will go over the 60-question review. Okay, take care, everyone. Bye-bye.